Okay, guys, so this is a brief recap of section 10.1, which is on polar coordinates. Let's begin by recalling some real numbers. Here are some examples of real numbers. 3, -5, pi. Pi is a real number. How about like 1/2? The square root of 7, 0.1. These are numbers that are called real numbers. Now, before we discuss other types of numbers, you have to remember something, a quick recall. So remember that the imaginary unit is called I, where, so that's I, where I squared is -1. So go back to your high school days. Maybe you remember from class where the imaginary number, we can have imaginary numbers. And the imaginary unit is called I. And just as a bonus fact, I squared is -1. So up here we have some real numbers. What are some examples of imaginary numbers? So these are real numbers above. Here are some imaginary numbers. So how about like, let's say I. How about -6i? How about 3/2 I? The square root of 11i. And going back to the real numbers, how about I squared? I squared is a real number because I squared is -1. So you see real numbers and imaginary numbers. Now, the reason we mention this is because the following question arises. What happens if you take a real number and an imaginary number and you combine them together? So if I take something from here and add it with something from here, we get a completely different type of number. And that leads us to another definition. So let's jot down this definition. So definition. A complex number takes this form. It looks like x plus I, y. This is what we call a complex number, where this part here, this is what we call the real part, and the part in the back, that's what we call the imaginary part. So that's what a complex number is. A complex number is a number that has two parts, where one of the parts is real and the other part is imaginary. That's what a complex number is. So what if we do some examples where they ask us to graph or to plot a complex number? So example, plot each complex number. So let's say for part A, we go 5 plus 3i. So I know it's tempting to say, hey, 5 plus 3i, isn't that just like 8i? But that's not how this works. We don't play the game that way. You see, these cannot be meshed together into one thingy because this is real and this is not. So it stays apart like that. It's one number with two components. Now, here is how I actually graph this. You go to the axes, but instead of x and y, it's actually not the xy axis. This is what we call the real versus imaginary axis. And so what you do is you go to 5 for the real, you go to 3, positive 3 for the imaginary, and you put a dot, you put a point at that location. Boom, done. final answer. This point is how you plot this complex number. How about this one? How about negative 2 minus 4i? So here we have a complex number. It has a real part. It has an imaginary part. And so what we do is we go to the axes, the real, and then the imaginary axis. And then we go negative 2. We go negative 2 for the real, and then we go down for the imaginary. And done. Final answer. That little point is the graph of that complex number. And what about example C? They might try to play you. They might try to trick you in the homework, on the final. Like this, watch. What if you have to graph? What if, for example, C, you see something like pi I? How the heck are you going to plot the complex number pi I? Well, first of all, I would rewrite it so that it looks like all the others. I would rewrite this as 0 plus pi I. And then pi, let's call it 3.14-ish, right? Just an approximation. And so now I know how to plot this. Go to your axes, real versus imaginary. So this is 0 for the real, so you don't move sideways at all. The only movement you make is up, 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 3.14 spaces, which is close to that location right there. Done. What about this one? What about, like, let's say negative 2? How the heck am I going to plot negative 2 on the complex coordinate system? Well, rewrite it, negative 2 plus 0i. So that would take us negative 2 on the real, and then nothing on the imaginary, right there. So with this warm-up in mind, now we can move on to the main idea in this section 10.1. So let's get this off the board. And let's develop this, let's unfold this idea from scratch. So here's an idea. Draw the first quadrant. And let's put a point up here, and let's call this point CPP. And let's say that you are right here. That's you right there. But you're trying to go to Cal Poly because you got to go to class. Now, how the heck can I go from where I am to Cal Poly? So can we agree that one way to go from here to there would be to move to the right X spaces, and then to go up Y spaces, and ta-da, you're in class. You went to the right, and then you went up. And X and Y, that idea of going left and going right and going up and going down, the idea of moving along these lines, left, right, and up and down, that idea is what we call, it's a rectangular movement. Let me check my camera. Make sure you guys can see back there. It's a movement that is what we call rectangular. And the reason we call it rectangular is because the rectangle is like left and right and up and down. It's like a box. So if you move along the grid like that, X and Y, that's a rectangular movement. However, here is a completely different approach that'll transport you from here to Cal Poly. What about the approach where you go whoosh, straight to Cal Poly? Like if you take the streets, you might use a lot of gas. Isn't it probably faster just to go directly from point A to point B? Isn't it faster just to go whoosh, straight there? And here's how you do that. Before you go from there to there, first you have to align yourself in the correct direction. And then you can go out. So the first thing you have to do is you have to open to the correct direction. You have to open some angle theta. And once you've done that, here with orange, Once you're facing the right spot, you then go to your destination. Let's get rid of that color. Let's try this in red. See that? And this we can call R. So this is a completely different approach. Instead of X and Y, what we can do is we can open an angle and then go out R spaces. So X and Y is rectangular, and then R and theta, that's what we call polar, which is the name of this whole lesson. It's a motion, it's a movement that's polar in nature. And now what I want to do is I want to create some relationships between R, theta, X, and Y. So for that, why don't we remember sine and cosine and tangent? So can you tell me what sine of theta would be? What would be the sine of theta? Sine is opposite over hypotenuse. So sine of theta would equal y over r. And let's say that we wanted to get y by itself. To get y alone, we could multiply both sides by r. Put an r there, put an r there. These are gone. So y would equal r sine of theta. What about cosine? Cosine of theta would equal x over r. And if you multiply both sides by r, x equals r cosine theta. And why don't you bubble in these relationships, because they're going to help us for the next part of this video. So we've just discussed the relationship between rectangular and polar. Rectangular is when you move left, right, up, down. Polar is when you open a certain direction and then go outwards R spaces. And here are the relationships between X and Y and R and theta. So now we can jot down some facts, some definitions. So now for this part, we can call this polar forms, complex number in polar and rectangular forms. Here we go. So a fact. A complex number can be written in two ways. Okay? In two different ways. So one way for you to write a complex number is what we call rectangular form. And that's what we wrote down earlier in this video. That was x plus iy. That's rectangular. But then, what did you just bubble in with, in the previous video, in the previous part? We said that x equals r cosine theta. We said y equals r sine theta. So, and that's what takes us to polar form. X gets replaced by r cosine theta plus I, and then y gets replaced by r sine theta. But if you notice, both of these terms have r in common, so it's traditional to take out the r to the front. And this is what we call the polar form of a complex number. So let me erase the version above it, because the version beneath it is the best version, and it's the version we're going to use. So now for the rest of this video, we'll do a couple of examples where you have to go from here to there. I give you something that looks like rectangular, and you have to do some math to turn it into polar. So let me see if I can get rid of this top part here. So let me get rid of all this, and maybe we can just keep this here for now, so we look back at these guys. So let's do two examples real quick here. So the directions are convert to polar form. Let me make sure the video looks good still. Let's see, does it looks okay. Let's move this up a little bit. So look, it says convert to polar form. Leave it there. And let me write this up just in case you guys can't see it. I know it's toward the bottom of the video. Let's leave that there, and let's get this out the way. I think that looks pretty good now. It looks okay. So, example A. How about like 3 plus 4i? So this is a complex number, but right now it looks like rectangular, but nuh-uh, bro. We want polar. I want to go from here to there. That means you have to find r and you have to find theta. We're going to have to find r. We're going to have to find theta. Once you know r and theta, you take those numbers, you plug them in there, and you're done. Finished. Here's how I would do something like this. Plot this number. Make a graph of it like you did just a couple moments ago. Go to the axes. And let's draw this a little bit bigger. Go to your real imaginary axis and plot the number 3, 4. I think I can actually draw it over here. Plot your number, your complex number 3 and 4. And it's over there. And why don't we make a right triangle out of this? Let's go like that. Let's go like this, where this here is 3, that's 4, and there's your right angle. And let's just make this solid. Doesn't really matter. There we go. So we have a right triangle. And then the hypotenuse, we can call it r. The hypotenuse is going to be called r. And now let's find r by using the Pythagorean theorem. So we can go like 3 squared plus 4 squared equals r squared. Do that and you're going to get 5. R is going to be 5 for this problem here. R is 5. And then all you have to do now to finish this problem is find theta, which is that purple angle right there. So to find theta, maybe we can go like a sine or cosine, and then maybe use like an inverse. So let's see. We know that sine of theta would be 4 over 5, because sine is opposite over hypotenuse. And then take the sine inverse, right? That's how we get theta alone. We go sine inverse of the left. We go sine inverse of the right. Let me grab my calculator. And we go sine inverse. Make sure you're in degrees. Sine inverse, and I get about 53 degrees. So these cancel. And theta is about 53 degrees. So folks, you're done. You can now go from rectangular to polar. Just tell me what r is. R is 5. And then cosine. And then theta is your angle, which was 53 degrees. Done. That's how you go from rectangular to polar. You find r and you find theta. End of story right here. Final answer. Now, this can get trickier, so we should really do one more problem before you go. So let's get this all off the board. And for the next one, we'll take it to a different quadrant. So let's get all of this out of the way. Let's try to do all this problem on this side. So how about now we do something where it ends up in quadrant number 3. So let me give you, just make this up here. Let me give you something like, let's say like negative 5 minus 2i. And we want to turn this into polar form. So make a picture. Let's go 1, 2, 3, 4, 5, 1, 2. And so we would be like right here. And then we'd go like that there. If we took the streets, we'd be like that there. This is -5, and this is -2. And then you can go Pythagorean theorem. You don't need me for that. Pythagorean theorem would tell you that r is the square root of 29. Just make sure in your papers you put the -2 in parentheses. Put the -5 in parentheses. And that'll give you square root 29. And why don't we prepare our final answer? My final answer, r cosine theta plus I sine theta. My final answer would be like square root 29 and then cosine of something plus I sine of something. I'm going to bubble this in because this is going to be my final answer. The only thing left to find is the angle, right? That's what we have to find. I need to know what goes right there. What goes right there. And I know that it's this. Look, look, look. It's going to be that. That whole purple angle, whatever that is, it goes right here. Now, before we find it, what are the, what do we anticipate? Can you guess that purple angle, between what and what? It's more than 90, and it's more than 180. It's more than 180, but it's smaller than 270. So I expect a number for this purple that's bigger than 180, but smaller than 270. So here is what we're going to do. With this red marker, I'm going to think of, instead of theta, think of a different symbol like alpha. Let's call this angle here, let's call it alpha. What you have to do is find alpha. And then once you know alpha, we'll do something to alpha, and that'll be our main angle, this purple one, which we can call theta. So first, focus only on alpha. Tell me what this angle is. It's a cute little baby angle. Let's find its measure. How can I find alpha? Maybe go sine. Look, sine of alpha is, well, sine is opposite over hypotenuse. Go sine inverse of both sides. These cancel. And so alpha is about, let's see, where's my calculator? Sine inverse of -2 over square root 29. Look, my calculator, it says like -22. Let me just focus it real fast. My calculator, it says -22 because the calculator, it doesn't see what you and I see. It's kind of blind. You see, I know that alpha is a positive angle, but this guy says negative because it's kind of confused. It doesn't know where we are. So whenever you come across that situation, all you have to do, look, make it positive. You see that? You and I understand where we are and what we're trying to do. Sometimes the calculators don't see what you and I see. So let's just turn this into the absolute value. So 22 degrees for alpha. And that makes sense because it's a cute little baby angle. However, I want theta, which is everything. You see, alpha is only this part there. But I need everything that came before it. And everything that came before it was a semicircle 180. So I need 180 plus the additional 22. So really for us, our theta is 180 plus 22, which is about, like 202 degrees. And that completes this problem. 202 degrees. Done, done, done. End of story. Now, before you go, you should really ask yourself, what if we were in quadrant 4? What if we were in quadrant 2? Because you might see that on the final exam where I give you a number and that number is maybe in quadrant 2 or in quadrant 4. You'd have to know what to do for your angles, to get the correct theta. And we might do that on the next video, so you really want to stay tuned for that one. So if you have any questions, just let me know. But if not, I hope you all have a wonderful Thanksgiving, and I'll see you guys soon. Bye.